All right, section 5.8 is the conclusion of chapter 5. We started in 5.7 talking about inverse trig functions and their derivatives. Now we're going to do the inverse trig functions with integration. And they aren't taking like arc sine, arc cosine, and finding the antiderivatives of those, but they're taking what those pieces were and finding the antiderivative of each of them after that. So we're getting back to the arc sine, the arc tangent, and the arc secant. So these are our three forms. You do not need to memorize these. These are not going to show up on your antiderivative gateway. We'll talk more about how this works for the exam as well. So feel free to just hang on to these and work with these, not to memorize them as you're working on your homework. So we do have three of them. So we have 1 over the square root of a squared minus x squared. So you notice the constant is first and the x is second in that. The second one, arc tangent, is 1 over a squared plus x squared. There's no square root, so that's unique to that one, right? The other two have square roots. And then on the third one, we actually have the variable x in front, and notice that the x squared is first underneath the radical and the a squared is second. And it does matter because it's subtraction, right? So the order of subtraction matters, so these orders matter as well. You might also note that the arc secant ends up with the absolute value of x over a on the right-hand side. And as always, we have plus c's on the end, and you're all going to put plus c's on your gateway, right? Absolutely. I anecdotally talk about a student I had. It's been many years ago. He had every question right, and he left off plus c on every question as well, which means he had to retake the gateway because that's the rules, right? So clearly he knew what he was doing, but I bet he never misses a plus c on something like that in the rest of his life because, it was a big deal. All right, so we're going to find some integrals, and in particular what we're trying to do is we're trying to match them to one of these forms. So you're looking for radicals, right? That's one identifying feature of which of the pieces you're looking at. And then you're also looking for the order of the x's and the a's, potentially. And of course, they're not going to be exactly these. They're going to have variations to them. So we're doing something like this. So we have 1 over 4 plus x minus 3 squared. So if this fits one of the forms we just learned, and it does, which form would it have to fit for sure? The second one. How come, Andrew? As opposed to what else? Let me say it this way. There's no square roots. Yeah, there's no square roots on this one, right? So no square roots means I'm not in 1 or 3. I've got to be in 2. Okay, so if it fits one of these, it fits number 2. Process of elimination is really important because you don't want to feel overwhelmed. And if you can eliminate something, it at least narrows down your choices. So it is going to be option number 2. In order to sort of match this together, though, we need it to be in the form that we saw on option number 2, which was the tangent one. So let me write that form that we're looking for right here. We're looking for it to say 1 over a squared plus x squared. That's our form that we're looking for. So the a is simple enough to deal with. What is a in this problem? A is close to 4. It's 2. A is 2 because 2 squared would give me 4. So if I were to sort of rewrite this and try to get it into the right form, 2 squared is what I would have here. So a is the 2. Okay, is everybody okay with that part? All right. Well, what about the x? Well, the x isn't just x here. It's x minus 3, right? So it's not going to be a very exciting u substitution, but I am going to do a change of variables so you can see it, that the u that we're going to use here is x minus 3. And the reason I say it's not very exciting is because what's the derivative of this u? 1. That's why I say it doesn't make it very exciting. It's 1 dx. So when I come up here into this problem that we're starting with, we have a plus here, and then I have a u squared here, and then the dx gets replaced by du. So we do want to get it into the form that sort of perfectly matches the form of one of those 3 on the previous slide. This one's the arc tangent. And once I have that, I can move into the fact that this is the arc tangent. Now, what came before arc tangent? 1 over a. And what is our a? It is 2. So ours is 1 over 2 at the beginning. After tangent, what came? X over a. So our x is now u. So it's u over our a, which is now 2. And then I need a plus c. The only thing to do then is to turn it back into the x variable that we began with. So I have x minus 3 on top over the 2. going to put it in parentheses because at this point it looks kind of messy with that subtraction. And we have our plus c.
So is there a reason why there's not inverse trig functions of the cosine?
Yeah, there's a good question on that. Do you remember when we took those derivatives? They actually looked a lot like one another. They were just different by signs. Some of them were positive, some of them were negative, those kind of things. That's why that's happening. Yeah. So did everybody hear his question? Why do we have these three and where are the other three? That's a reasonable question. We had 6 of them before. Why do we only have 3 of them now? It's because of the way that those derivatives actually came about, and they had mirroring images. They were just opposites of each other. They were in pairs. Do you remember doing that last time? Yeah. If you don't, it's okay. But they were in pairs, and so that's why that's happening. Okay, let's try another one. All right, I do have a square root this time, which means I'm not in case number 2. This is not arctangent, correct? No, it's not. Yeah, so you're exactly right, David. It's going to be arc sine. What clued you into the fact that it's arc sine?
Because there's nothing outside of the square root.
Yeah, there's nothing outside the square root, right? The denominator has a square root and nothing in front of it. Does that make sense? Cool. Now we need to identify the pieces. So again, we will do the same thing we did before. Let me write the form up here so that I'm not flipping back and forth. I have 1 over, I have the square root, I have a squared minus x squared. So we'll start out first with what is a. So what is a in this particular problem? Yeah, it's 5, right? Is that all right? Now, let's say it wasn't a really pretty number. What if it didn't say square root or it didn't have 25, it said 27? What would we do? We just do square root of 27, right? So it doesn't have to be a perfect square for this to work. It's easier to see it when it is, but it doesn't have to be. Okay, good deal. All right, how about the x? What is our x? It's the tangent part, right? So I'm going to relabel it like it on the last one as u. Okay, so what is u? Is it tangent squared? It's actually just tangent, right? Because the squared is part of the form we're looking for. We want it to be x squared, or in this case, u squared. Like our goal is for this to say minus u squared, so we have tangent as our u. But what is the derivative of tangent? It would be secant squared. That part you know from last time you know from lots of times, but we did it last time on your gateway, right?
And so we converted it to 1 over the du.
So there's a 1 here, and I have du out here. These pieces, we'll change color here. These pieces right here all get connected. That's the du part. We'll put the 1 on the top of the fraction and the du at the end, so we've got replacement. And then it actually looks exactly like what we want it to look like, doesn't it? It does. So our arc sine is what's coming about now. So this is very nice. There's no coefficient in front. That's friendly, right? It's just the arc sine of x over a. So ours is now going to be the arc sine of x, which is our u, because our variable is u at the moment, over a, which is 5. And we have a plus c. But then we want it to be in terms of x because it began in terms of x, and u is tangent of x. So it looks kind of funny. It says arc sine of tangent of x over 5, right? I've got the arc sine of a tangent. So we've manipulated with that a little bit. If that 5 weren't there, we could actually simplify this more, and we could turn it into some triangles, and we could simplify this into a different expression. But because it's both arctangent and it's got the over 5 part, we're just going to leave it. Okay, so this is the arc sine of the tangent of x over 5 plus c. Okay, so just like we were doing in other sections, we kind of just hit on all the bases, right? So we've done the integration, that's the plus c's. This one is going to be the definite integral. It's got limits of integration, so we have to take that into consideration. Which of the trig, arctrig functions or inverse trig functions does this use? It's arctangent again. How did you know? There's no square root in the denominator, right? So you probably thought I was going to go with the third one because we hadn't done one yet, right? So don't get tripped up and think that it's all equally distributed. That doesn't always work. This is arctangent, which is 1 over, let me get it written right, a squared plus x squared. Okay, so what is our a? 1. It's a really nice a on this one. What is our variable? And we'll call it u. E to the power 2, or e to the, hang on, let me slow down. E to what? Just e to the x. Yeah, e to the x, sorry. I got ahead of myself. Okay, so this is one of our new derivative rules, right? For this year anyway. What's the derivative of e to the x? E to the x, he's your best friend. And then we have dx at the end, right? So we can take these pieces and we can replace them now. We don't want to write the limits of integration. We're going to leave them off because we're changing the variable into u's. Those numbers apply to x, and x is not written in my problem anymore. So I have 1. I know it's 1. I'm going to write it as 1 squared. So forgive me if you don't like that, and don't do it if you don't want to. But I think it matches things nicely, so I'm going to write it. And then I have plus, and it's e to the x squared. So I called it u. Do it that way. U squared. And then the part at the top will become a 1, and we'll put the du at the back. All good? Okay, so we're going to take the antiderivative of this, and from your front page, this is going to be 1 over 1, and then arctangent of u over 1. And we would put a plus c if we were going to stop, but we're going to eventually put in our limits of integration, so I'm not going to put the plus c because eventually it'll cancel out if I do. So I'm going to leave it off for now. I'm stopping, at this point I'm going to stop writing all the ones that are sort of silly to write. Okay, so I'm just going to write this as arctangent. And what was u? E to the x. Okay, is everybody good so far? Okay, now that it's back in terms of x, I can replace the x with the values that it is equal to. That's loud, isn't it? Nice. Okay, so the x limits of integration are 0 and natural log of 5. Okay, so we're going to put in these values. So now I have the arctangent of e to the natural log of 5 minus the arctangent of e to the 0. Now, when we plug these numbers in, sometimes they're not going to simplify, and sometimes they are. And you really need to figure out when that happens and when it doesn't. And your calculator is not always all that helpful. Okay, so remember, arctangent of values is giving us angles, right? We're looking for angles, and they're in terms of radians, which means if they're nice radian values, they're going to have pi in them, which makes them irrational, and your calculator is not going to give them back to you in a way that you can use very well. Is everybody with me on that? Okay, so we have to use some of the things that we know about trig. We also have to use some things we know about inverse functions with e's. So do you see that e to the natural log? Do you remember how we simplified that? Yeah, the e to the natural log of 5 will just be 5. So this part at the beginning is just the arctangent of 5. Okay, now, if you get arctangent of 5 and stick in your calculator, it's going to give you an ugly decimal. But consider this. If you think about your unit circle, do you ever, like unit circle values you memorized back in the day, do you ever find tangent values that are equal to 5, right? Y's over x's. No, you don't find anything like that. So when we get to this point on the arctangent 5, there's nothing else to do, okay? That's not going to happen on the other part of this problem. The other half of this, we're going to simplify further. What is e to the 0? 1. So this is the arctangent of 1. Now, there are arctangent of 1 values on the unit circle. Okay, so here's what I want you to remember. I'm going to jot this down over here. We'll change colors to remind you that this is sort of deviating back into trig. If we're doing the arctangent of 1, and it's equal to some angle, we'll call it theta. This is the same thing as saying that 1 is equal to the tangent of theta. Okay, so where on the unit circle do you get tangent values that are 1s and negative 1s? Do you remember? Pi over 4s. So either pi over 4 or negative pi over 4 if we were dealing with a negative one, right? Tangent, we looked at this last time, is going to be defined to be in quadrants 1 and 4. And this one says tangent of theta is 1. So we're going to be in quadrant 1, which means it's going to be, you had said it first, pi over 4. So this theta value right here is pi over 4. So if we have the ability to change it, we're going to. Arctangent 5, we had no ability to do that, so we leave it. Arctangent of 1, we do. So we're going to write it as pi over 4. Now, it's possible the WebAssign will let you leave it as arctangent of 1. I don't know what it's going to do, but I can assure you on any quiz or test that you do for me, if I saw arctangent of 1, there'd be a point associated with changing that into pi over 4, because that's material we've seen before, even if it was a while back. Okay, is that all right? Okay, cool. All right, let's take a look at the last one then. I'm going to find the integral. And now it's got a phrase in here that everybody knows and loves, complete the square, right? And it says if necessary, but you notice that that wasn't in the other direction, so it must be necessary at this point for me to throw it in, right? Okay, so why in the world, first of all, might this be an arctangent? Well, the first thing that you might notice is that if you tried any other tool you have, like u substitution, if I let u be what's underneath the radical, the du wouldn't be there, right? Because the gut reaction a lot of times that we have is we're going to use u substitution because we've been using it a lot. And we do. It's one of our basic tools. We do use it a lot. But if I let u be negative x squared plus 4x, and I try to do du, it's simply not part of my problem. It's not there. So this doesn't work. Okay, so if you did this on the test and you saw this doesn't work, you don't need to erase it. Just mark it out. You've tested something. You found it didn't work. Now test something else. Right? That's the idea at this point. So the next thing we would try, because again, we don't have very many tools, would be to take a look and see, is it one of these arc-trig functions? We know it's not tangent because there's a square root. So which of the two is it? One more back. Is it arcsine? It looks like it, right? Because I don't have anything in front of the square root again, right? So it looks like it's going to be an arcsine. But arcsine tells me that I'm supposed to have this form. And that's definitely not the form that is currently underneath the radical. Agreed? It's even got a linear function x in there, right? That linear term in there. There's nothing about this that's supposed to have a single x by itself. I'm supposed to have a constant squared, and I'm supposed to have an x squared. I'm not supposed to have an x. Okay, is everybody tracking with me okay? Okay, I want to develop in you the reason for why we're doing this. It's not just because it's like fun. I mean, it's fun, but that's not the reason, okay? All right, so that's what's going on, is that this should match something because it's the only other tool we have right now, and it doesn't quite. So we're going to take this piece, and we're going to manipulate it until it does. In particular, notice that the x is at the end, and it is supposed to have a negative in front of it, and our x does have a negative. So that's a good sign. I mean, that's a good first step. It is the right sign on the x. So what we're going to do next is we're going to manipulate the complete. Actually, let me do it this way. Let's just talk about what's underneath the radical. I have this in my notes, and I like it. So let's just look at what's under the radical, and then we'll put things back in when we need to. So underneath the radical, we have negative x squared plus 4x. Okay, so we'll start with that. Completing the square. Completing the square has you add or subtract things in pairs, right? So if I add 4, I have to subtract 4. If I were working with an equation, I can add 4 to the left and I can add 4 to the right. That's another way of doing it. But I don't have an equation. Equations have equal signs and this doesn't. I have an expression. So whatever I'm going to do is going to be balanced by an addition piece of it and a subtraction piece of it. Everybody good? Okay, I need that negative there, but I need that negative pulled out in front. So I'm going to pull the negative out, which is going to change the signs. And one of these red lines is going to be inside, and one's going to be on the outside. Okay, that's the balancing piece I'm about to do. That should have said minus 4x. There we go, x squared minus 4x. The key to completing the square is to take this middle term, divide it by 2, and then square it. It's always the linear term divided by 2 and squared. Notice it actually doesn't matter if it's negative or positive because it gets squared, right? So that part of it wouldn't have changed even if I had mistakenly continued to write the wrong sign there. It will change something else later on that will make it wrong, but it wouldn't have changed this part. So what is negative 4 divided by 2 squared? It's 4. So this key right here, I'm going to move it over here to remind ourselves it's a 4, which means I need to have a plus 4 right here. But I didn't really add 4. I subtracted 4. Why? Because there's a negative in front, right? Everything in parentheses has a negative in front of it, including the 4 I just put there. So I really inserted, if you will, up here, if you think about my line that I did up here, a negative 4. So if I balance this, what would I need to do on the red line on the outside? I need to add a positive 4. So it looks like I'm adding 4 twice, but I'm not. One of them is a positive 4. That's the one on the outside. The one on the inside is a negative 4 because it has a negative pull to the front. Okay. So then, why do we like completing the square? What does it do? Well, it factors things into perfect squares. So remember I mentioned a minute ago, square root of 25 is really nice because we know that square root of 25 is 5. But if we had 27, it'd be okay. It'd just be ugly, right? It's kind of like this. This will have a square root, but the prettier square root is one that's perfect. And that's what we're achieving by doing completing the square. So if I have x squared minus 4x plus 5, it will perfectly factor into x, and then the sign comes from the middle term, minus, and then the square root of the last term, 2 quantity squared. Okay, it'll factor into x minus 2 times x minus 2, a perfect square. Now, it's close to how I want it to look. Look back up at the radical where I'm trying to get to. What's wrong, or not quite right yet, about the radical piece I have underneath right now? What's that? They're added together, kind of.
Well, you just move the 4 to their side.
Okay, say that later. Yes. Okay, so I want my x at the end, and I want it to appear as subtraction, which it will, because there is a negative in front of the x piece. So I'm going to take these two pieces, and I'm going to swap them. Right? I'm going to write them in the other order. I'm going to move the 4 to the front, and I'm going to have the minus and the x minus 2 squared at the back. Is that okay? All right, I'm going to go back to the original problem now, and I'm going to put that in. So I think I might have actually, yeah, I do have an extra slide, so I'm going to go up and I'm going to write this again. So the original function looked like this. Negative x squared plus 4x dx. And the work that we have just done will actually change the way it looks into 4 minus x minus 2 squared dx. Okay, is that all right? Okay.
You missed your 4, I'm afraid. The 4x, you missed the x on the first equation.
Here. Thank you. All right, cool. Gotcha. My mind was not processing. Thank you for bearing with me. Okay, is that all right? Okay, so we're looking at the one on the right now, and we're trying to identify the pieces that match, right? The pieces that match what our goal is. So our goal, remember, is to get this written as 1 over the square root of a squared minus x squared. And we're awfully close. What will our a value be now that we've done all this manipulation? It's 2, you bet. What will our u value be? X minus 2, which is, again, not a very exciting u substitution because its derivative is 1. But that's okay. We can have not exciting sometimes. The 2 that's on the top will just stay a 2. Or if you don't want it on the top, you can put it in front of the integration symbol. Okay? So I often like to put mine out here. Just pull the 2 out. I'm just going to leave it where it is, though. There's no reason I have to pull it out. The part on the bottom now is the square root of 2 squared. And then plus minus u squared. Okay, so coefficients, this is a 2, they come along for the ride, right? When you're taking derivatives, they just are part of the derivative. When you're taking antiderivatives, they're just part of the antiderivative. So that 2 will come along for the ride as well. We haven't had this show up in any of the other 3 examples yet. It's just going to be there. So it's going to be in front. So if we had wanted to move it in front of the integral, that would have made it sort of nicer looking maybe a little bit. And then we have arc sine. So it's supposed to be arc sine of u well, x over 5. X is our u, or u is our x, over a, rather not 5, a. And our a value is 2 on this one. Yep. And then we would have plus c. I'm just going to put the plus c at the very end. It doesn't matter if you put it inside and distribute the 2 to it, just creates a different constant, but it's some constant that it's added to at the end. But we don't have u, not really. Our arc sine value will be the arc sine of u, which is x minus 2 over 2, and then plus c. Okay, any questions on that one? Definitely the most complicated. Had to manipulate a lot more with the completing of the square in that step. So some of them are going to have that, some of them are not. I'm going to have that, but just sort of be on the lookout. Okay?